Imagine this. You're making ice cream, or perhaps just need some ice cubes fast. You have two bowls of water. One scalding hot, the other icy cold. Which one will freeze first? Every fiber of your being screams the cold one, right? But what if I told you? You're wrong. What if hot water can actually freeze faster than cold water? This isn't science fiction. It's a real, documented phenomenon that has puzzled scientists for centuries, and it's called the Mpemba Effect. Our story begins in 1963, in Tanzania. A schoolboy named Erasto Mpemba was making ice cream for a class project. He noticed that his hot mixture, which he put directly into the freezer, froze before his classmates' room temperature mixtures. His teacher dismissed it, but Mpemba was persistent. Years later, he shared his observation with a visiting physics professor, Dr. Dennis Osborne, who eventually helped him publish their findings. But Mpemba wasn't the first to observe this. Ancient philosophers like Aristotle, Francis Bacon, and René Descartes all noted similar anomalies. For centuries, this quirky observation was largely ignored or attributed to experimental error. Mpemba and Osborne, however, brought it back into the scientific spotlight, sparking renewed interest and countless experiments. The Mpemba effect directly contradicts our intuition and basic thermodynamic principles. How can a substance that needs to shed more heat to reach freezing point possibly get there faster? It's like saying a marathon runner starting miles behind the pack can still finish first. The scientific community has proposed numerous theories, but none have been universally accepted as the definitive explanation. One leading theory suggests that hot water evaporates faster, reducing its mass. With less water to freeze, it cools more quickly. The loss of volume means there's less total energy to dissipate, accelerating the freezing process. However, experiments have shown the effect can occur even when evaporation is minimized or prevented, so this isn't the whole picture. Another popular idea involves supercooling. Cold water can often be cooled below its freezing point without actually solidifying. It needs nucleation sites to start forming ice crystals. Hot water, it's theorized, might have fewer dissolved gases or impurities, or its heating process might destroy some nucleation sites, allowing it to supercool less, and thus freeze more readily once it hits 0 degrees Celsius. Convection currents play a role too. Hot water has more vigorous convection, meaning heat is distributed more efficiently throughout the liquid and expelled faster from the surface. As it cools, the colder, denser water sinks, pushing warmer water to the top to be cooled. This enhanced heat transfer could give hot water an edge by rapidly shedding heat from its entire volume. Dissolved gases are also considered. Hot water holds less dissolved gas than cold water. These gases can act as insulators or hinder ice formation. Furthermore, the freezer environment itself can affect things. Hot water might create a thicker layer of frost underneath its container, improving thermal contact with the freezer shelf and enhancing heat transfer. This frost acts as an insulating layer for the cold water, slowing its heat